In this video, we're going to talk about arc length, which is really a combination of some pretty interesting things, limits, Pythagorean theorem, and thinking about integration. What I put up here at the top is an idea that you learned in Calc 1, that if I have a series of rectangles where I get the height by multiplying the function by the base times height, or base times height, and I add up all those rectangles and I increase the number of rectangles under the curve, then that limit as n approaches infinity is the true area under the curve represented by the integral. And you looked at that proof in Calc 1, so I'm not going to go back into it now, but it's important to think about that this series, this addition of all of these rectangles, delta x being that base, this kind of becomes a dx. Dx represents this delta x getting smaller and smaller. Okay, so arc length. How would you approximate a line segment connecting the two endpoints? Well, I think the easiest way to do it, and again, the key word here is approximate, is you would say, well, I would connect the two, right? And I'd have a change in x and a change in y, and I would use Pythagorean theorem. Yeah. Change how much x changed, how much y changed, and that would do it. Now, of course, that's an approximation. If you said, well, how would you make the approximation better? Well, to make the approximation better, we would simply do Pythagorean theorem more. Maybe break it into two segments like that. Of course, the more segments we break it into, the better our approximation would be. Okay. Now, I want to play with some algebra with this Pythagorean theorem, and remember that what I could really do, though, is do a sum of all of these little segments. And I'm going to leave that idea aside for a minute, but I want you to keep thinking about it. It's still Pythagorean theorem with a delta x and a delta y, but now it's a sum of a bunch of little Pythagorean theorems. Okay? Let me play with some algebra. So, I'm going to take my Pythagorean theorem that I wrote down. I'm going to factor out a delta x squared. I think you'll see why here in a minute. So if I do that, I'm left with 1 plus delta y over delta x squared, like that. Now, a delta x squared I can pull out and have delta x, the square root of delta x squared, like that. Okay. Well, as you add more and more rectangles, delta y over delta x approaches the derivative. So that 1 plus. And from up here, from up at the top, as we take the sum of more and more of these little Pythagorean theorems, this delta x becomes dx. So this arc length formula is the integral of the square root of 1 plus the derivative squared dx. Okay. It really is just a sum of an infinite number of Pythagorean theorems. Let's try a couple. So here's the formula as it says in your book. Arc length is the integral from a to b of 1 plus the derivative squared. So find the length of the curve, 3x squared, on the interval from 3 to 7. So the first thing I think I would do is find the derivative. Okay, so if f of x is 3x squared, f prime of x is 6x x. So my arc length, I have the integral from 3 to 7, the square root of 1 plus 6x squared dx, which we could rewrite as the integral from 3 to 7, square root of 1 plus 36x squared dx. Now, a lot of times on the AP exam, these are calculator questions, or they're kind of a matching, like which of the following would find the arc length. I just want to point out, this one actually you could probably handle with some trigonometric substitution. It wouldn't be a pretty integral by any means, but you could handle this by drawing the triangle and labeling the sides, 6x and 1, and you could actually do this problem. I would just use my calculator at this point. It's a definite integral. We're not looking for the antiderivative. We're just looking for a numeric answer. So I would do fn int on this function from 3 to 7. Okay. All right, let's do another example. Find the length of the curve e to the 3x. Well, if f of x is e to the 3x, we need the derivative, which would be 3e to the 3x. So my arc length would be the integral from 1 to 5 of the square root of 1 plus the derivative squared, which you could rewrite, and I don't think I would necessarily rewrite it. I mean, especially if you're just going to use fn int to find the answer, I would probably just type it in directly as I wrote it. But if you needed to simplify it a little bit, it would look like that. And let's just visit, 3 squared, of course, is 9. An exponent to an exponent, we multiply, so 3x times 2 becomes 6x. So these are the two integrals, and many times, as I said in the AP exam, that's what's asked. Which of the following integrals would find the arc length? Okay. Now, what this arc length idea gives us the ability to do, though, is some pretty cool things with shapes that we haven't been able to do before. Let me show you. So I did a video a little bit ago using this shape from an old AP exam, and it was finding the area of R and S and doing some revolutions, and you could build some cross sections and so on. But it's all volumes and areas. But now, knowing how to find arc length, now I can begin to find perimeter. All right, so I'm going to just move this down a little bit, and knowing that I'm going to use arc length because I'm finding the perimeter, I'm going to need the derivatives. Okay, so if f is 1/4 plus sine of pi x, let's find f prime. So that's 1/4, of course, derivative of that is gone. Derivative of cosine, or sine, is cosine. We're thinking chain rule, so leave the inside alone, then multiply by the derivative of the inside. So there's that. Okay. Now, the derivative of an exponential equation we don't use a whole lot. Okay, it's that same exponential equation multiplied by the natural log of the base, and of course because it's a negative x, we're going to put a negative out front of this whole thing. So that's our derivative of g. So to find the perimeter of R, let me just kind of highlight that, what that would be. This would be the perimeter of R. We've got 3 sides. Now the first side, I'm going to erase that so I can actually see. The first side right here is from 0.25 to 1. So the first side is just 0.75 units. We didn't need any arc length to do that. The next side, let's maybe go here, we're going to integrate from x equals 0 to x equals 0.178. The square root. Now that function, that blue function, is g, so it's going to be 1 plus the derivative of g squared dx. Extend that a little bit. Okay, so this integral right here gives me this blue side right there. Okay, let me add on the next side. Of course, here we're going to integrate from x equals 0 to x equals 0.1782, but now it's the red curve. So it's going to be the square root of 1 plus the derivative of f. Squared. And you would do these in your calculator using fn and that would give you the full perimeter of the shape. And that's kind of exciting to be able to find the perimeter to go along with the area. I mean, these are geometric ideas that we've been talking about for years and years, and now you can actually use calculus to find these perimeters with curves. And it's not something that is necessarily one of the huge topics in calculus, but it's kind of an important idea. All right, let's quick find the perimeter of S as well. Of course, now it's only two sides. We only have these two sides, these two lengths that make up S. So we're going to have an integral from x equals 0.178 to x equals 1. It's going to be the square root. I'm going to do the top curve first. Not that it matters, but I'm going to do that first. So it's going to be f of x, or f prime of x, excuse me, squared. And then the other integral will be 1 plus g of x, g prime of x, squared. And again, you could use your calculator to calculate those, and that would give you the perimeter. This actually has appeared on the AP exam a couple of times. Most times it just says, in terms of integrals, write out the equations that would find the perimeter of the shape.